So our next speaker is not me. It's Tian Liu, I believe. And they are from Texas A&M. I think it's no surprise that there might have been a visa issue or that they just really love Texas. Stall again? Okay. And you may have noticed I am not actually Fred. I'm Pei. I'm from University of Michigan, just so there's no confusion. This is why you thought I was better looking than what you think Fred actually was. More? Zoom is working. I will try not. Oh, so Tian is here. So he will tell us about his work on Eric. Or maybe not. Oh. Yes, he will.
Hello.
We're not seeing your slides yet, if I need that.
Yeah, let me see if I can share my screen.
So what that happens when, just a note for everybody, if you ask a question, please say your name and affiliation. So we all know.
Sorry, I think there's something wrong with my screen sharing.
Okay, we see it. We see
can you see my screen?
Yes, we see your screen. Yeah.
Oh, great. Sorry, let me see. What about now?
It works.
Can you see my screen?
Yes.
Okay, great.
Go for it.
Hello, everyone. My name is Tian Liu. I am a PhD student in the Computer Science Department at Texas A&M University. I would like to first thank the CHAOs and conference organizers for helping us set up the remote presentation. And it's my great pleasure to present you our work, Eric, estimating rainfall with commodity doorbell cameras for precision residential irrigation. And our work is collaborated with the Department of Biological and Agricultural Engineering at Texas A&M University. And to begin with, I would like to introduce the motivation of our work. So our work is motivated by the substantial water waste in the current irrigation system. According to the U.S. Environmental Protection Agency, they report that the landscape irrigation accounts for 1/3 of U.S. outdoor water usage, totaling over 9 billion gallons per day. But however, as much as 50% of water are wasted due to inefficient water methods and irrigation systems. The significant waste of water motivates us to develop more efficient and precision irrigation systems. And now let's first take a look at the limitations of traditional irrigation systems. So on the left, we have the typical irrigation system that operates in a set it and forget it philosophy. This type of system, they operate in a fixed schedule without considering the environmental factors such as the rainfall, solar radiation, plant and soil types, which causes significant waste of water. And to improve the efficiency, people have been using soil moisture sensors to directly monitor the water content in the soil and start the irrigation when the water contents drop below a certain threshold. However, these sensors have limited measurement range, which is just about 12 inches around the probe. And these sensors require frequent calibration to the temperature, to the soil salinity, etc., incurring a high maintenance cost. Due to these limitations, many US states have widely adopted the weather-based scheduling. The weather-based scheduling methods considers the water balance between the incoming water and also the outgoing water. So as you can see in this plot, the incoming water includes the rainfall, the irrigation, and the outgoing water includes the plant transpiration and evaporation. And these methods calculate the irrigation amount by simply taking the difference between the evapotranspiration and the rainfall. As you can see, these methods relies on accurate rainfall measurement for a nearby weather station. And in practice, homeowners, they usually receive weekly irrigation from the government agency and adjust their irrigation valves manually. And to improve the precision of irrigation guidance, the government has spent a lot of money building dense weather stations to obtain more accurate rainfall measurement. For example, on the left-hand side, you see that the Water My Yard program in Texas, they have built over 50 weather stations across the states. However, we still see large space between the weather stations. And in fact, our field experiments show that the rainfall measured from a nearby weather station that's only 1.7 miles away can differ as much as 54% from the actual hyperlocal rainfall at the residential site. The inaccurate rainfall measurement significantly affects the irrigation efficiency. So now the question is, how to improve it? How can we obtain more accurate hyperlocal rainfall measurement? And in this work, we present our solution, the Irrigation system, which harnesses the existing doorbell camera to obtain more accurate hyperlocal rainfall estimation. And our idea is that the doorbell cameras, they are widely available, and we would like to explore the multimodal information, including both the visual and audio features captured by the video recordings for better hyperlocal rainfall estimation. And before I introduce how we estimate rainfall from the camera, and here I would like to first introduce our Irrigation system. As showed in this plot, we have the doorbell camera that is streaming continuous video and audio data to the irrigation controller board. And the controller board processes the video and audio features and uses a pre-trained neural network model to estimate hyperlocal rainfall at the edge. And the estimated rainfall is then used for optimizing the irrigation schedules, and the controller will then activate the sprinkler accordingly. And here, I would like to emphasize a few advantages of our system. So first, it can obtain accurate hyperlocal rainfall estimation through machine learning models. And then it has high system efficiency on processing continuous video streams in real time. In addition, it preserves user privacy by conducting all the training and inference at the edge. It also has low hardware cost by harnessing the existing doorbell cameras, and also we only use a simple Raspberry Pi 4 device for the controller board, which is only $75. And finally, this system, it runs irrigation scheduling fully automated without requiring the user's manual intervention. And now let's look at how we can estimate rainfall with camera. Existing methods, they fall into two categories. The extraction-based methods, which tries to extract more accurate raindrop shapes using some geometric and photometric methods. These methods, they require not only tuning the camera settings for optimal visibility of the small raindrops, they also face significant challenges in practice. So for example, as shown in this tube image, the raindrops at the further distance actually creates a rain fog effects and are not visible to human eyes or to the camera. And also there could be some residual water on the camera lens, which may block the views. Moreover, the wind may also distort the raindrop shapes. And in the example on the right, during the nighttime, we cannot even see the raindrops due to the poor light conditions. And recently, people have also explored the deep learning-based methods using the CNN model for rainfall detection and estimation. However, these models require large amount of training data and expensive GPUs, which are not currently available to homeowners. They have also lacked rigorous evaluation on continuous streaming videos because they mainly test their model on some randomly split raining images retrieved from the internet or some synthetic raining images. This is probably due to the insufficient open source video data about rainfall. So now we have two challenges. The challenge one is how to develop a model that is accurate and also generalized. By generalized, I mean we do not need to tune the cameras for a specific camera for specific backgrounds. And also it needs to be robust to different environmental factors like the lights, like the wind, etc., etc. And the second challenge is that how to achieve high efficiency and low compute cost for processing video streams. These two questions actually drive the design of our methods. And to address the first challenge, our key intuition is that instead of focusing on the actual raindrop shapes, we can actually estimate the rainfall from the reflections. And here, the reflections, as defined by the equation on the left, is the absolute intensity change between two adjacent video frames, which captures the fast-moving objects, like the raindrops, between the video frames. And interestingly, as we can see in the figure on the lower left, we see that we can even capture the splashes of water from the ground, which is also a good indicator of the rainfall intensity. Based on the reflections, we found that the intensity and density strongly correlates to the rainfall intensity. For example, we see more reflections during the heavy rain, and on the top right, we see during the light rains, there's much sparser and less reflections. And comparing with the top row and the second row, we can see that the reflections also works during the nights, and also works at different environment backgrounds. And more importantly, we do not require a carefully tuned camera. A simple commodity doorbell camera will work, can capture the reflections. So that's how we adjust challenge one. In addition, we also find that the audio data provides helpful information for rainfall estimation. And as everyone has heard about rainfall, during the heavy rain or during the light rains, the rainfall actually introduces a repetitive drum hitting sounds. And the heavy rain actually leads to the increased amplitude and frequency of the audio waves. And as shown in this plot, during the heavy rain, which is marked in the green box, we see a lot of peaks. And the magnitude of these peaks actually corresponds to the intensity of the rainfall. So that's why we want to leverage the audio features. And another advantage of the audio features is that they are not restricted by the camera inputs. So we do not need to worry about the camera settings, light conditions, background, etc. So the audio features provides additional help in addition to the camera visual inputs. And now let's look at the second challenge, how to adjust the significant compute cost. So to address this challenge, we designed simple neural network models for rainfall detection and regression. And here we show the pipeline for our algorithm. So as you see, given a video, our model first extracts the visual and audio features, and then we combine the features and pass them to a rain detector to predict whether the minute is raining or not. And then we also pass it to a rain estimator, which estimates how much it rains for a minute. And finally, the results are aggregated to obtain the final cumulative daily rainfall. Here, importantly, we use simple neural network models, which are multi-layer perception models. And this model, it has only 2 hidden layers, and each layer has only 6 neural nodes. And because of the simplicity of the model, it can be trained, and it runs inference efficiently at the edge without worrying about the high compute cost. And here is just a quick summary comparing our methods with existing methods. Our reflection-based methods does not need to tune the camera. It can achieve high accuracy, high efficiency. It also works at night. And more importantly, it preserves the user privacy because we do not upload the video to the cloud. And next, we present the evaluation of our system. So to evaluate our system, we deploy it to 5 different residential locations with diverse background, light conditions, camera setup, camera types, camera placement. We collect over 750 hours of video data for training and evaluating our model. And comparing with previous extraction-based methods and deep learning-based methods, our model actually achieves lower errors, which means it can actually captures the rainfall intensity much better. And on the right, we show the comparison of the ground truths, which is the red lines, with our ERIC model, which is the blue lines. We see that our prediction matches the actual rainfall intensity accurately. And also we see that it works not only for heavy rains for the top rows, but also works for the light rains on the bottom rows, despite that it may be affected by some human movements in the video, but we still see the overall performance is pretty good. And also we check the memory and the latency. We see that our Eric can run real-time inference at the edge. And finally, we compare how much water we can save. So by comparing with using the rainfall data measured from a nearby weather station, which is shown in the blue bar, and our Eric system, which is the green bar, we can save over 9,000 gallons of water for the August. And then in another case for the September, we see that we actually supplies desired amount of water to prevent turf damage. And finally, for the conclusions, we developed an end-to-end irrigation system, ERIC, which estimates rainfall from commodity doorbell camera for precision residential irrigation. And compared with prior rainfall estimation methods, ERIC is accurate and robust. It is efficient. It is also low cost and privacy preserving. And our field evaluation shows that ERIC actually achieves state-of-the-art rainfall estimation performance and saves over 9,000 gallons of water per month. That's translating to $29 of utility savings per month. So with that, I would like to thank you all for listening, and I'm happy to address any questions you have.
Thank you.
Thank you.
Any questions? First question, can you hear us?
Yes, I can hear.
Hello? Oh. Hello, Dongyin Lee from UC Merced. I would like to ask how the Ring camera how did you collect the training data for this Ring camera information? Did you use your own data set? Did you make your own data set, or did you use a data set from the public data sets?
We actually collect our own data set. So if you're seeing the deployment image on the left, we have the actual ring gauge. The reason why we use our own data set is because there's no public available accurate video data with accurate rainfall measurements. That's why we have to collect the video data set ourselves.
Did you deploy multiple Ring cameras near the same location to see if there's any variance to the rain data estimation, or?
That is a great question. We only deploy, so currently we only deploy one camera at each residential location. I guess another way to validate the effectiveness or robustness of our methods is by deploying into different residential backgrounds. So as you see on the right, we deploy it to different backgrounds, and also we try different camera taps, different camera placement, and it matches pretty good. Yeah, thank you for the question.
Hello, thank you for the great talk. I just have one question. Do you have any deployment constraint on how you deploy the camera? Because it seems like, oh, your camera in the deployment always pointing outward. That might not be the case in all of the deployments.
I'm sorry, I didn't catch your question. Can you explain your question again?
Yeah. So my question is like in the deployment that you show, your camera is always pointing outward. That might not be the case all of the deployments. Did you test it like, okay, the angle of the deployment, does that matter, or how much that impact your reading?
Yeah, great question. So as you see on the right, we show the different camera views from different residential sites. We actually have different deployment, like we deploy the different camera placement. So you see like on the lower left or the lower right, we have limited views of outside backgrounds. So I guess the question is more about like, does the background affects the rainfall estimation performance? I think the answer is yes. So from our experiments, we see that the reflections, they are usually more obvious or more stronger when we have darker background. So for example, if we have a building, let's say on the top left, we have a building in the further distance, and the roof of the building is like black, right? So from that area, we can actually see more reflections. So the reflection does matter, but as long as there are some like reflections, either from the dark background or there's some light source. For example, in the lower left, we have two LEDs. The reflections from the LEDs can also help get to obtain the reflections. So does my answer your question?
Yes. Thank you
Thank
so
you.
much again for the presentation. I apologize you couldn't be here in person, but not my fault. Thank you again.
Yeah, thank you. Have a good day. Yeah, hope to see you in person. Thank you.
Okay, so our next speaker